So as I sent an announcement, first make sure you've checked with the solutions I posted. Then if you saw inconsistencies on Friday, go to your respective TAs on either of the labs, and then they are able to update the grade. About question 1A and that question for the for and while loop, what was that, 4? So for these two, I need to discuss with TAs, and I'll let you know guys the final outcome, because if you have to accept both cases, it need to be for all of them. If you don't, it doesn't have to be any change. So for these two, we're gonna make an announcement. Other than that, if you found any inconsistencies, go talk with your TAs on Friday. All right. So many grades has been changed. So this will be changed as well. But for now, the average for lab 1 was almost 18. So these are the histograms. So the majority of the students, so these are the number of students, like 30, 25, 20. So the majority of the students are among who had from 14.4 up to 19, and also 19 to 24 for lab 1. For lab 2, we had a lot of students from 18 to 24, and the average was 18.1 for the lab. Okay? So this is from 30. If you see a number from 100 on Moodle, because Moodle tries to just extrapolate this number and make it scale from 100, so just it's not a big deal for now, because that's going to account only for your 30% of the grade. The rest of the grades are going to be from your labs and your final. Okay, so just look at the grade of its own. Do not look at from the 100. If you want to see the performance by question for lab 1 and lab 2, so these are the distributions we had. So question 1 up to question 6. This is the highest point and the lowest point. And you see these boxes, we call this plot box plot. So the line in the middle shows the average of the grades for each question. So that the average grade for question 1 was around 2.5. Question 2 was around 2.5. Question 3 was 2. Question 4 was around 3. 5 was 2. And 6 was 4. Okay? That's for lab 1. For lab 2, the range was a little bit smaller, but similar for the rest of the questions. In general, I guess the difficulty of your exam was very moderate. Like, it was very easy exam. Don't you think? One more thing before I hear your feedbacks. I received a comment about question number 5, and that we couldn't read a C code. Okay? While that's true, the reference book for your course, we were just following the reference book, and on this book it was written in C. The other point that I made sure that just like one of your colleagues asked in the exam, can we write this in Java, and I approved it. But for this question number 5, if you just use an online converter from C to Java, you write. So that's the code for question number 5. Okay. If you convert it to Java, you're gonna see the exact same thing, except that you're gonna have a private or public static there, right? So the fact that you didn't understand this because it was in C, to me, doesn't seem very accurate, because the Java code was completely equal, right? And I made sure I asked you a question that is very simple. It was only 2 lines. Did anyone had issue on this question just because it was in C? Okay. So by tonight or tomorrow, we're gonna make an announcement for question number 1A, and also that while and for loop. Okay. So give me your feedbacks.
No, it's just I also asked about 1B, and I believe the solution for 1B is not correct. So
1B.
you might take a look at that.
If the performance evaluates in the same criteria, then the 1B should also be measuring instruction per seconds.
Okay, I'll have a look at that as well. Also 1A and 1B. Yeah. Oh. Yeah.
I posted on the Moodle asking about, like, if we could see how 1A and 1B were found, so we can look and find out for ourselves how to do that if we got it wrong, because only a number is answer given.
Okay. Okay. So yeah, for one A, yeah, okay. I'll make sure I'll do that. Okay. Sure.
People say there's C and B instead of A.
Yeah, that. So who had number 1A correct?
No.
So you had it correct? You had it correct? All right, I'll have a look at it tonight, and I should talk with the TAs about perhaps something was wrong in the solution. All right, anything other than 1A and 1B?
What happened? Nothing.
Yeah, I'll make an announcement for that. No worries. Any other feedbacks? I mean, of course, if you want to send me anonymous feedback, you can. You always send me some emails that I don't understand what the name was. We can always do that. But if you want to have a public feedback, that's the time. Yeah. 3A? I'm not sure what that is. It was 40, I believe. I'm not sure. I can't recall what the question was. Really? I should send me an email. I'll double check it. Okay. Yeah. There's no way, guys. What is it? Can we solve 2A using MIPS instead of RISC-V? I don't hear you. So you had the correct answer. You can go talk with the TA on Friday. Yeah. So that's one case.
Sorry for this question. We're supposed to allocate these things for four of those functions.
I'm not sure what the. Did you see the solution? Two? Yeah. So perhaps two. I mean, you could have allocated more, but it wasn't necessary.
Based on the steps of the textbook, all the arguments
When I correct the paper, I'll have a look at it. Okay. Any other concerns or feedbacks? Okay. So we're gonna have only 20 minutes. Let me just start with the Appendix A of your book, because tonight and tomorrow you're gonna have some time to play around with Verilog and Icarus, and also on Wednesday I'm gonna carry on with this. We've already started chapter 4 2 weeks ago, but this is just another sort of introduction on how you're gonna deal with your labs. Okay, I've posted the lab 2 days ago or yesterday, so you have this week to work out and see how does it work. Install the compiler if you're not using the lab machines, and then start working on that. Okay. So in logic design, normally we set a convention that 0 volt. Okay. So when the power is on or when the power is off, we're going to consider it as logic 0. Okay. On the other side, when we have the power on, so depending on the circuit, it's going to be either 5, 1.5, or depending on the system, we're going to have a logic 1. So since most computers are using a smaller voltage now, instead of 5, for instance, they're using 1.5 in the newer generation. So we just consider it the other way. So we just consider it as logic 0 or logic 1 instead of mentioning the specific voltage. Okay. All right. So these were the gates you've already seen some lectures ago. So we have the standard AND here. So two inputs comes. The AND of that would be the output. This is the OR gate, right? So it's going to make an OR with the two inputs. And then this is an inverter. So whatever comes here is going to be a negative. So it's going to be a negated output. It's going to, if it was a 0, it's going to be 1, or if it was -1 or 1. If it was 1, it's going to get to the other side, okay? So these are the gates normally we have. And there are different ways to write that inversion, right? So on the left side, either you're going to write it this way with that triangular and that bubble there, or you just omit that and then make a bubble here, a circular. So both cases, it's going to show that the signal A comes and it's going to get inverted, and then you're going to have an OR at the end. You're going to have another inversion, okay? So both ways is correct. So we can stack them up and have multiple inputs. You just have to follow the lines and see which of them crosses which. For instance, you have 4 A, B, C, and D, right? You have 3 ANDs, and you just have to see which of them crosses which. So here it's going to receive as input A, B, and C, and it's going to AND those, right? So AND of A, B, and C is going to be A, B, C. It's like a dot, like a multiply, logical multiply. Here, those that crosses the second AND is B, C, and D, right? So you're going to have B, C, and D here. The third one only receives A, C, and D, okay? And it's going to make an AND. So that's why you have C, D, A. So these are the ANDs. These are the okay? What about these pluses? The output of these are going to get fed into an OR gate. That's why you have pluses here, okay? So you have ANDs there. The outputs are going to get OR, all right? So simply by combining them, we can implement more complex logic. Let's talk about other gates. I already mentioned that the little circle means not, so an inverted gate. This is an inverted gate for OR. So this is an OR that gets inverted at the output. That's why we call it NOR, right? Or not OR. Just like this for AND, right? When we invert after the AND function, so we're going to have NAND or not AND. And the rest of the two are just receiving more input already inverted. So we're going to see them in the next slide. Okay? So for this one, it receives 3 inputs now, right? So input 1, input 2, and input 3 are receiving AND, and the output would be 1 on all cases except the case that all of the inputs are 1. Okay, that's a NAND gate with 3 inputs. All right. In logical system, we have 2 different sort of high-level systems. One, we call it a combinational logic. The other one is a sequential logic. Mostly, we're going to focus here on the combinational logic here. So a logic system whose blocks do not contain any memory, right? And hence, we need to compute the same output given the input every time. However, the sequential logic can contain memory, all right? So as an example, remember we had truth table previously I was showing it to you. So given 3 inputs, because they are binary, right? You have 3 inputs, A, B, and C, and you have outputs there. Given 3 inputs, you have 2 to the raise of 3 entries because these inputs have different permutations, right? All of the 3 could be 0 up to the point that all of the 3 are 1. So from this to that, you can play around with 6 more lines, like 0, 0, 0. So the third one is only 1. The second one is only 1. And the first one is only 1. Then you have the second and third one, first and third, and first and second. So if you permute all of those, in general, when you have a binary system, depending on the number of input, you have 2 to the raise of that input as the output. So 3 input, 2 to the raise of 3 is going to be 8 lines, okay? And for instance, in this case, that combinational logic block is going to represent us the output as follows. D will be true only, D would be true if at least one input is true, right? So the case that D is true, you can see that at least one input was true. Here, here, here. E is true if exactly 2 inputs are true. So there are exactly 2 inputs. And also F is true if all the 3 inputs were true. Okay, this is one way to showcase some outputs given input, right? In a truth table. Yeah.
So all of them can never be 1. Like,
All of the inputs can be 1. The last
I
one.
mean, like all of the.
Oh, input and output. Yeah, in this case, no. Yeah, yeah. But the inputs can always be 1. Yeah. All right. Just like this, we can define and implement so many different blocks. Okay, logic blocks. But first, let's have a look at some rules, some Boolean algebra rules. Okay. First of all, we have an identity law which states that a plus 0 is a. Right? If you add 0 to a, it's going to be still 0. On the other side, if you multiply with 1, it's as if you didn't do anything, right? It's going to be still 1. The second law is 0 and 1 laws. You add 1, you're going to receive output as 1. You multiply by 0, you're going to receive a 0. Okay? These are just simple laws. You've already seen it perhaps in your basic algebra. Also, just like that, we have a commutative and also associative law. You can play around with the order a plus b is equal to b plus a, and also the dot, right? For the dot, a dot b is equal to b dot a. And also the more sophisticated one is like a distributive law, so that you can distribute this a among all those parentheses. So a dot b plus c could be a dot b plus a dot c here, okay, and the other way around. Finally, we have inverse laws that if you add 1 with its own inverted 1, you're going to receive 1. So a plus negated 1 or inverted 1 is going to be 1. And if you multiply it to its own inverted, it's going to get to 0, right? We have 2 more laws that you're gonna see. Perhaps you've seen it elsewhere. So they are famous as De Morgan's law. So the negation of conjunction of 2 propositions. So when you have 2 propositions Q and P, when you negate the conjunction, so this is the negation sign, and this is the conjunction sign, right? It's as if it's equivalent of the negation of disjunction, right? If you negate the whole, the conjunction, the and becomes or. And that's the truth table for that. You can see that's the starting point for P and Q for both cases, true and false. And then that's the negated version of either of those. Then that's the conjunction of those. That's the conjunction of a negation. And then you're going to see that it's going to be the same as the other side, which is the disjunction of the negation. Okay, so that's the Morgan's law number 1. You have the other way around for number 2 of the law, which is the negation of the disjunction is going to be equivalent to the conjunction of the negation. So it's just intuitive on the other side. Okay, so these are just very basic. I'm just trying to recap them before you start your labs. So in general, De Morgan's law states that a plus b, all inverted, which is a negation, is going to be a negated multiply b. And the multiplication would become addition here, okay? All right. So then we have programmable logic arrays, or they stand for PLAs. They can be programmed, okay, and can implement any logic function, okay. So let's see what are the categories of these PLAs, okay. So in general, we can define any logic function, right, with only and, or not function. You just have to stack them up and build them together to just make it more complex. All right, so the standard component for PLAs are decoders, multiplexers that you already seen in chapter 2 and 3, and ROMs. So for decoder, it's a logic block that has n bit input. In this case, it has 3 bits input. Okay, and it's going to output 2 to the raise of n, and we call it as we're going to decode the input. All right, so that's your input, a 3-bit input, I1, I0, I1, and I2, right? So by each of those inputs, you're going to decode one option from the 8 option of the output. Say if you pass 0, 0, 1, you meant that I'm going to have my first output, right? Because 0, 0, 0 is like 0. If you were to pass 1, 1, 0, 1, it was referring to the line 6, because 1, 0, 1 refers in binary to 6, right? So that's why you have n-bit input. Using that n-bit, you can expand to 2 to the raise of n-bit in the output. Okay? It's very intuitive. All good so far? But also do make sure that only one output is asserted at each input. Yeah.
What do they use in the decoder?
So sometimes, for instance, you wanna pass your processor to do a specific action, right? You just you use that 3 number or 4 number, and it's gonna decode up to, like, if you use 4 numbers, you're gonna just command it up to 16, right? Like add, multiply, do this, branch. All right, multiplexer. You've already seen that. We also use the term selector previously for that. So you're gonna have, it's a control signal that is used to select one of the input values of a multiplexer. So the difference between this and a decoder is, in decoder you just pass it several input at one, like 3 bits, 4 bit, or 1 bit, and it's gonna output once. But here, it's gonna only select one of the signals of the input. It multiplexes, right? It's a selector of either, in this case, either A or B to be outputted. Okay. And the last one we talk about today is the ROM. You've already perhaps heard the word ROM. It's a memory that is generally not writable. You can write it once. Recently, we have some programmable ROMs as well that can be programmed. Also, we have some version of ROM that are erasable. But mostly, what we focus here is a memory that has a set of locations fixed like this, and it's only working as it was programmed. Okay, so that's called a ROM in general. Regarding the definition of optimization, it's that when 2 different logic expressions can have exactly the same behavior, right? However, 2 different expressions with identical behavior may have different costs of implementation. So which one to choose? So that's the optimization part. We normally want to have the one that has the lowest cost, right? And that's the concept of optimization. In this example, you see both of them are going to give you the same output, right? But one of them will cost more. Okay? right? Does that make sense? All right. I'm going to stop right here, and on Wednesday we carry on this introduction. Do make sure to attend your labs either tonight or tomorrow, and start working on your pre-lab.